Hi guys, Daniel here, and today we're going to do an AIME problem. And this is 2011 AIME number 1 problem number 7. So let's first read the problem. Find the number of positive integers m for which there exists non-negative integers x0 through x 2011 such that m to the power of x0 is equal to the sum from k equals 1 to 2011 of m to the power of xk. Now before doing this problem, let's first understand what it's trying to say. So this summation notation might be kind of bothering, so I'm just going to expand everything out. This is equal to m to the power of x1 plus m to the power of x2 plus dot 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 plus m to the power of x 2011. So what this problem is basically saying is that we have to find all positive integers m such that a power of m is equal to the sum of 2011 other powers of m. So this still doesn't seem that easy to do. So let's just investigate on how to represent m to the power of x0 in terms of some number of powers of m. So let's take m to the power of x0. How can we represent this as the sum of some other number of powers of m? Well, the most basic thing we can do is to represent this as m times m to the power of x0 minus 1. And this is equal to m to the power of x0 minus 1 plus dot 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 plus m to the power of x0 minus 1. And there are m of these powers of m. So let's see what the change of the number of powers of m we have. So here, let's say number of powers of m. Here we only have one power of m. M to the power of x0 equals m to the power of x0. So there's one power of n here, but in our new representation, there are m powers of m, which is m copies of m to the power of x0 minus 1. So is this the smallest increase we can have? Well, clearly, since m to the power of x0 minus 1 is the next smallest power of m, that the smallest number of increased powers of m that we can have happens when we have a bunch of these powers. But the smallest number of m to the power of x0 minus 1s that we need to have in order to make m to the power of x0 is clearly m of them. So for any change into a smaller power of m, it changes from one of the bigger powers of m to m of the smaller powers of m. So an overall m minus 1 increase in the number of powers of m. And this is the key observation. Because we could do this exact same thing for any power of m that we choose. For example, if we choose this power of m, this is in fact represented as m to the power of x0 minus 2 plus a bunch of these, m to the power of x0 minus 2, and we have m of these that make a 1m to the power of x0 minus 1. And we see that there are already m powers of m to the power of x0 minus 1, and one of these is changed to m powers of m to the power of x0 minus 2. So the total number of powers of m in this case is, well, we already have m of them. We subtract 1 and add m, so the total number is 2m minus 1 powers of m. And so in general, we see that the number of powers of m that we can have to represent m to the power of x0 is in fact 1 plus k times m minus 1, where k is the number of substitutions we made from a higher power of m to a lower power of m. So at first we have one power of m, namely m to the power of x0, and then we have k substitutions from a higher power to a lower power, and each of these substitutions increases the number of powers of m by m minus 1, hence giving this formula. And then finally we know that the total number of powers of m is in fact 2011 from our original problem here. So now we just need to solve this system, this equation. So first we can move the 1 on the other side. And now note that k and m-1 are both integers. So in fact, we can solve for all possible values of m by simply factorizing 2011 and finding the number of factors of 2011, or 2010, sorry. So in this case, 2010 factorizes as 2 times 3 times 5 times 67, and thus, by taking the powers of each of its prime factors and adding 1, then multiplying together, we can find the total number of factors of 2010, which is simply 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 equals 2 times 2 times 2 times 2, which is 16. So there are 16 factors of 2010. And every single factor gives a unique value of m that works. And finally, we know that only these values of m work, because every time we make a substitution, we must add exactly m-1 additional powers of m to our sum of the powers of m. So that means there are only 16 possible values of m, such that this original thing is satisfied. So therefore, the answer is simply 16.
Hey guys, I'm here back with another math video. Today we're going to be doing more AIME practice because of course the test is coming up. Today we're going to be doing problem 25 AIME